Close to the camera, Lee.
Hello, everybody, and welcome to this month's Future in Space Hangout. My name is Tony Darnell, and I'm with deepastronomy.com. I want to welcome you back to this hangout that we have on the third Friday of every month, and where we bring to you both engineering and science principles or science topics that are geared towards looking ahead beyond what we've already currently are working on in both science and space astronomy and space exploration, and look at not only the scientific challenges but the engineering challenges as well going into the far future. And we do that with the help of members of two organizations, the American Astronomical Society and the American Astronautical Society. We call upon their membership base to help us out and help understand, so it is with their generous endorsement that we are making these podcasts available. And this month we've got a really interesting one planned for you. We are going to be talking about the future of space astronomy, and that's a general term that I use to describe things that go into the space telescopes that are going up into space. It's not my term, other people have used it too. But as you may already know, and if you watch these podcasts, you certainly do know, or these hangouts, you certainly do know that we currently are operating the Hubble Space Telescope, has been up there for 25 years looking at the universe in a variety of wavelengths. It started out in the optical and the ultraviolet, and later on, as over the 25 years, has become more infrared-based, although it still remains the only game in town if you want to do UV astronomy, ultraviolet astronomy, with the instruments that it has on board. And of course, you've also heard us talk about, with my guest Alberto Conti, who's my co-host here, and I'll introduce him in a minute, with the upcoming James Webb Space Telescope, which is going to be primarily an IR telescope, an infrared telescope, and it will be much larger than the Hubble Space Telescope. Is scheduled for launch in October 2018. But there is a huge wavelength range that we would like to explore, and that's what we're going to talk about now. Astronomers from all over the place have gotten together, and we have two of them with us today to talk about these endeavors, about something that sounds French, but it isn't, LUVOIR. It is the Large Ultraviolet Optical Infrared
Surveyor.
Surveyor, thank you. That's what I was looking for. And it is a very big effort that's being done and put forth by people thinking about all wavelength ranges, not just the infrared. So with that, let me just before I get to introducing my co-hosts and my guests, I want to let you know how you can interact with us. If you have questions or comments for us, please use Twitter. It's our primary way we're doing it right now. The hashtag is right down below here, Future in Space. If you use that, I will be monitoring that. We've cut it back just a little bit, but I also, in terms of how you interact with us, only because we've been having some technical issues with the YouTube chat window. However, I will mention as a little technical note, that is being solved. I am working with others to find another way to have a live chat going on during these hangouts, and I hope to have that in place by the next hangout next month. So for now, if you could bear with us, just use Twitter, and I would appreciate that. As well as I used to have a this is embarrassing. I used to have an email address for this, but I can't seem to log into it right now. So don't email me right now. I can't seem to use it. So anyway, without further ado, let me go ahead and introduce my co-host first, and then I'll introduce my guests. Joining me, as they do almost every hangout, Dr. Harley Thronson. He's an astrophysicist from the Goddard Space Flight Center. Hi, Harley. Welcome back.
Great. Good afternoon. As always, glad to be here.
I'm glad. And I've noticed that Harley has his audio sorted this time, which is very helpful. Thank you very much. Oh, no, yes.
There you go.
Yes, that, by the way, is our gravitational wave rubber ducky. So
yeah, we need another one.
Yeah, we need another one. Okay, also joining me is Dr. Alberto Conti. He is the innovation scientist at Northrop Grumman Systems. Hi, Alberto. It's good to see you again, my friend.
It's good to see you both, Harley and Tony. Glad to be here.
Good. Thank you very much. And so my guests tonight are both from NASA's Goddard Space Flight Center, and they are looking ahead. They are looking to the future of space astronomy, primarily in in all of these wavelengths that I just mentioned before. So Dr. Aki Roberge, she's hi Aki, she's from NASA's Goddard Space Flight Center, as well as Dr. Lee Feinberg, who deals with a lot of the technical and engineering aspects of what we're going to be talking about. Welcome, folks.
Hi there.
Okay, so let's get started with the big picture, shall we? LUVOIR. Who wants to tell me what this is about? It might be Harley, but maybe Aki, if you felt like saying something about it, that'd be nice as well. What is LUVOIR? It's such a really cool sounding acronym.
Yes. So as you said, it stands for Large UV Optical Infrared Surveyor, and you know it's not the best acronym ever, but we're in.
I don't know. I think it's pretty cool.
And part of the reason it's not the best acronym ever is because we're in a concept planning stage. So right now, NASA has started 4 studies of big future space telescopes that would come, you know, after Hubble, after the James Webb Space Telescope, and actually even after the telescope that NASA is planning after that one, even after the thing called WFIRST, if you guys have talked about that.
Mm-hmm.
So these are long-range plans, and these concepts are being developed to be presented to the whole U.S. astronomical and technical community in 2020 under the direction of the National Academies, who will, you know, take a hard look at them and prioritize what basically all of the U.S. space science should be doing over the next decades. And so LUVOIR is one of these concepts. And the simplest way of thinking about it is it's a super duper Hubble that would span a huge range of wavelengths, as Tony already said, all the way from the ultraviolet to the near infrared, and it would have a wide range of capabilities, sort of like like a really excellent Swiss Army knife. But like Hubble, it would be able to, you could use it for many things. It would revolutionize pretty much, you know, practically every area of astrophysics that we're studying right now. But even more so, it would have the capability to have those general purpose capabilities that allow you to think of new things, new investigations that you had no idea were even interesting 20 years earlier. And in particular, also this time for LUVOIR, it has one really important and compelling prime science goal, and that is to really find the rocky planets in the habitable zones of nearby stars that are like the Sun, and look at their surfaces, see if those surfaces have habitable conditions, which is by our Earth standards, what that means is having liquid water on the surface. And then once we find those, to actually probe their atmospheres and to see if we can see the signs of that life is affecting that atmosphere. So these are what we call biosignatures in the atmosphere, and Earth's atmosphere is full of them.
Right. So I want to go back to something you kind of said in a as part of your description. You said look at these planets. Now that means actually physically resolving these things, not just finding them, because that's a distinction. That's right. That's right, and that's huge because we all know, we've talked about TESS before, the Transiting Exoplanet Survey Satellite. We also know that the JWST is going to be able to see these exoplanets, but they'll be able to detect them, but that's different than actually looking at them. And I wanted to make sure people could appreciate what we're talking about.
Well, a friend of mine, Scott Gowdy, likes to, he says it like transitioning, if TESS is the area, you know, if Kepler and TESS we're in the era of the small black shadows era for exoplanets right now, moving towards these direct imaging is from small black shadows to the pale blue dots, those actual pale blue dots of Carl Sagan's vision from decades ago. So.
Okay. Right. So Lee.
Even though they might not all be blue.
Well, no, they're not all going to be blue, but we want to find the blue ones.
Yeah, definitely.
Indeed.
We have a bias towards those for sure. So Lee, let me bring you in this on this. So we're talking about space telescopes that, in order to be able to image these things, what are some of the engineering things that go into thinking about a telescope like this? Presumably, we do have wide wavelength ranges, and they also be quite large, right?
Yeah. So LUVOIR, I mean, obviously the L in LUVOIR is large, and
so how large are we talking about compared to say JWST?
So we might be talking 10 to 12 meters is the kinds of numbers we've been looking at, and you know, the James Webb Space Telescope is a 6.5 meter telescope, and it's segmented. It has 18 segments in the primary mirror, And so we might be talking about having something that looks a little bit like James Webb, but imagine another 2 rings of hexagonally shaped mirrors, and again a system that would deploy, with wings, much like the James Webb Space Telescope. The difference, though, being, you talked earlier about Webb being an infrared telescope. Since this is more of a UV and optical telescope like Hubble, the mirrors won't necessarily be cold. And more importantly, it has to be a very stable telescope. It turns out actually the hardest challenge of finding these pale blue dots is that the dots are really dim. We're looking at reflected light. These stars reflect light off these planets, and because of that, they're so dim, you have to have an incredibly stable telescope, or the slight fluctuations of the mirrors would totally swamp those nice pictures. It's kind of like when you take your telescope out in your backyard and you look through the atmosphere and it's kind of blurry. That's kind of what would happen if we don't build a really stable telescope. And we go all the way to the L2 Lagrange point, the same place as Webb, which is one of the most stable places to put a telescope. And even then, we're still talking about almost 1,000 times more stable than Webb was. And so that's really the key technological challenge in addition to the size.
So we're talking about, as you said, telescopes at least twice as large as the James Webb Space Telescope is. But this idea of the stability I get, but to me it seems like also a big challenge in making these things is the wavelength range. You already mentioned that for infrared telescopes it's easy,
right?
Comparatively speaking, you just have to make it cold, but that's not necessarily. You want a wide range of operating temperatures as well at these different wavelengths, don't you? So you need to be able to dial in a lot of stuff when you use a telescope like this.
Yeah, I mean, in a lot of ways, the mirrors, the technological history from the mirrors is actually Hubble. Hubble, because the hardest mirrors to make often are the shortest wavelengths. So, and we need this to work in the ultraviolet. So the mirrors, the quality of the mirrors will.
Oh, that's an excellent point. They have to be reflective. With James Webb, again, it was easier, not easy, but easier because you could pick up a coating that was reflective in the wavelength range of IR. But that's not necessarily going to work in the infrared or even the optical, right?
Yeah, and so the performance in terms of the imaging performance of this telescope is about 4 times better than the Webb telescope. So it actually has to be what they call diffraction limited in the visible wavelengths, and which is similar to Hubble, but on a huge segmented telescope like Webb was. Webb is diffraction limited in the infrared, and that's kind of so now we're sort of pushing the performance of the telescope in terms of how well it images by about a factor of 4, and pushing the stability by almost a factor of 1,000.
Actually, though you didn't talk about the really, it seems to me anyway, that you didn't talk about the primary technological challenge, which is that the Earth is 10 billion times fainter than the Sun is, and it's located, if you're looking at it from interstellar distances, it's really close to that bright source. So it's like it's like trying to see the airplane as it's flying across the sun.
Right.
So the technology that we have to develop for this mission to enable that to take pictures of something really faint next to something really bright is these coronagraphs. And these are instruments that are, it's kind of like, it's like a fancy way of putting your hand over the sun so you can see something faint right next to it. And it's the requirement of doing that, what you call high contrast imaging, is what really is driving that stability that is needed for this telescope.
Okay, so Alberto has this concept drawing of the Atlas telescope. What does Atlas stand for again? Let's just put that out.
There's the Advanced Technology Large Aperture Space Telescope.
Thank you. So this, Alberto has a drawing up of what this might look like, and so it looks a lot like JWST. I see it has got segmented mirrors, but just more of them. The the shield there is enormous. Presumably, it's hard to get scale from the drawing here. But I'm not seeing anything to block out light. Where would that go, guys? Where would you see that?
It actually would go in an instrument, and which are sort of behind the primary mirror. And in fact, we have coronagraphs on the Hubble Space Telescope that are about 4 or 5 orders of magnitude too low a performance than what we need here. And the WFIRST telescope, which Aki was talking about, will plan to have a coronagraph as well. That's actually starting to get closer, about 2 orders of magnitude away from what we need here. So there is sort of a technological heritage on coronagraphs. The keys here are, the coronagraph has to be even better, about 100 times better than, or at least 10 to 100 times better than what they're going to be doing on WFIRST. But it also has to work with this segmented shape of the primary mirror, which is a little bit unique compared to even WFIRST. WFIRST doesn't have segments; it's a monolithic mirror, although it does have what they call struts. So they've solved some of the challenges, but not all of them. And so you mainly solve those challenges internal to the instrument, or you could use a star shade or some combination. And even there's still the possibility that we would use a star shade as part of this system, which is another way to block that light, but you block it externally. It would be in front of the telescope.
Okay, so let's talk about that a little bit. So in order. Okay, go ahead, Alberto.
I always interrupt you all the time.
No, I know that's
very
okay.
normal. I just wanted to say that I think what Aki and Lee have mentioned altogether, I just want to recap for 1 second, which is important at least for folks probably to understand, which is really the fact that this LUVOIR, whatever you want to call it, whatever the telescope is going to look like, it really depends on the heritage of the Hubble Space Telescope. It depends on the heritage of instruments that are going to go on WFIRST. It depends on the heritage on JWST. So it's the field is moving forward, little step by little step, learning from lessons learned from previous telescopes to build these massive telescopes that will eventually, tell us if we're alone in the universe, which I think is actually a very, very good way to understand the progress.
And don't forget ground telescopes, because
absolutely.
Yeah, I mean, even the current suite of ground telescopes and the future ones, 30-meter telescope, ELT, they all have coronagraphs.
Absolutely.
Things like CAC and TMT look a lot like these types of segments, and they are also working on some of these same problems, and some of the technology does cross over between the two.
Right,
Absolutely.
that technology would. However, they are limited. Ground-based telescopes are limited by the atmosphere and what wavelengths they can observe. Certainly, UV needs to be done from space, and that's a good thing. You don't want to be it's a good thing that the atmosphere blocks out the UV from getting down to here too much. So they are limited in that respect. So we've thrown a lot of terms out, and I just want to make sure we cover some of these. A coronagraph is a thing that it's a term that comes over from solar physics, and I worked in solar physics for quite a while. A coronagraph was something that was designed to block out the disk of the sun so that you could see the very thin, very dim, tenuous atmosphere called the corona. And so it was called. They sort of inherit that into this technology here. But the way it was done on the sun was they would put little tiny disks in the optical path that would be in the focus on the focal plane, and they would get rid of the disk of the sun or block it out so that they could see the faint things around it. And that's what we're talking about here: ways to block out the bright star's light. Now, because these apertures of this particular telescope is so large, we can actually resolve disks, can we? Is that right, Aki?
Disks of what? Disks
of stars and planets.
Resolve them like make maps?
Well, resolve them like see a disk.
See, all right. See that you're talking about seeing the planet like.
Well, yes, we're talking about looking at planets, and we're not talking about resolving the individual disks.
No, I mean
okay.
that's still way beyond that's still way beyond LUVOIR. If you were going to actually make maps, like resolved maps of an exoearth around another star, that's beyond LUVOIR.
Okay, so I misunderstood when I thought we were looking.
No, what we're talking about here really is the little fuzzy pale blue dot that Carl Sagan imagined, right?
I see, which is an unresolved point it's just a smudge, essentially.
So it's separated from the star, but it isn't. The disk of the planet isn't resolved.
Well, since we're on that quick topic of resolving, let me put this up as a backdrop to what we're saying. So this was an image that Aki sent me about what we're talking about. So these are maps, apparently. You could see the different kinds of simulations, of course. So these aren't real. Where you could see there's in the top row there's this hypothetical planet 9, which we've talked about with Mike Brown and his guys about what this might look like. And here we are looking at it in different resolutions. This disk here, this very fuzzy one, is how Hubble might see this, and then we're looking here in these other two disks at the LUVOIR, different diameters and how they can resolve it. Now, this is in our solar system, and what Aki was just telling me was that these other stars aren't going to be this resolved. But this is what I'm talking about. When you talk about resolving a disk, this is what I mean.
Yeah.
So
yeah, what LUVOIR will see for exoplanets, though, is more like what Hubble would see for a planet in our own solar system.
Yeah, and I think a really key point, though, is that, you know, one aspect of this is what you can image, you know, the picture you're talking about, which, as Aki mentioned, you know, we may need a future telescope beyond this to get really good images. But the other part of it is to do spectra, is to take spectra and to really understand the chemical composition of what's there. And that's really a key focus of LUVOIR, because to take spectra, you know, you need you need to collect a lot of photons in order to spread them out over their different wavelengths. Otherwise, you just don't have enough photons. And so a key part of LUVOIR is to really go after spectra at a level that we can, you know, discern oxygen and water, etc.
And that's not possible, or won't be possible, with James Webb Space Telescope, because it's also going to have spectroscopic capabilities, but not for red wavelengths.
Not for planets that are truly Earth-like.
Okay. So what are we talking about with James Webb then? James
Webb will be able to do fantastic spectroscopy of a whole range of giant planets and sub-Neptunes and maybe some super-Earths. But even the super-Earths that JWST can do will be very different in very different environments and very different themselves from the Earth. They'll be a lot hotter, and they'll be bigger, they'll be hotter, and they'll also tend to be around smaller, you know, lower mass stars, red dwarf stars too. So to go after the real true Earth analogs that are like Earth size with that are primarily rocky, Earth size in the habitable zones of sun-like stars, which, you know, we think we understand better, JWST can't do that. That's, you know, hence LUVOIR.
Yeah, and JWST really, what it's doing is it's looking at what are called transits. So it's kind of looking at the atmospheres as the planet passes in front of a star.
Right.
LUVOIR is really looking, because it's trying to look for these small rocky planets, it's looking at reflected starlight. And that really is the technological challenge. When Aki was talking about this contrast problem, the reason we need a coronagraph, it's because LUVOIR is trying to look at reflected starlight so that we can see Earth-like planets around, you know, G and K stars that are more like the sun, as opposed to doing transit studies of these bigger, you know, maybe super Earths at best, but bigger planets.
Okay, so Lee and Aki, then let me take that a little bit further. So you're saying that, like, so the measurement that JWST will make this of starlight passing through atmospheres, is that a less desirable or a less accurate measurement than the ones we're talking about here with looking at reflected light off of the star? Is that a more desirable measurement?
It's different. You know, it's better for different kinds of planets. Now, you know, all kinds of exoplanets are interesting, you know, and JWST is going to do a lot on that. And furthermore, it's actually a good training ground just for us to learn more about exoplanets, you know, because there are lots of different kinds of exoplanets out there that are very completely different from the ones in the solar system. But to really do like the true Earth analogs, the planets that we think are actually like the Earth, that can't be done. And around sun-like stars, that can't really be done with transit spectroscopy for a couple of rather complicated technical reasons. So for that, you have to go to taking real direct images of the planets instead of looking at them passing in front of the star.
Okay, good. And that sort of goes along. Getting a comment from John O'Meara on Twitter. He's saying that it's important to note that you can't resolve the planet, but you can get spectra of its atmosphere, and that's what we're talking about now. Right. So yeah, and that was so when I initially heard look at planet, I was thinking, oh my gosh, we're going to be actually doing this resolving thing, and apparently it's just a little bit different. That we want to block out as you say, the technical challenge is to block out the starlight so we can get these reflected measurements.
So when I say resolve, that means we're separating it from the star for the first time.
Okay. That is resolving. It's just it's slightly different than what I had envisioned. Yeah. So can we talk a little bit about the timeline, because I want to kind of clarify that a little bit. As most of you know, space, especially with exoplanets, it works a little bit like this. TESS goes up August 2017, right? And then we've got James Webb Space Telescope, October 2018. that will operate for, these will operate for their mission lifetimes on the span of years. Then we've got what's coming up, which we've mentioned a couple of times. We haven't really defined, but we have had other hangouts on it. WFIRST, which is the Wide Field Infrared Survey Telescope. It's going to be looking at a much larger area of sky. That's next after JWST, sometime in the 2020s, I believe.
Right.
And then what we're discussing is after that. What comes next? And really, we've got a lot in the infrared on deck, but now we're talking about expanding these wavelength ranges to a much wider range, which I think is extremely exciting. So I want to talk about that, but before we leave this idea of blocking the sun, let's talk. Lee, you mentioned this. You mentioned this before. Starshade. This is another technology that can be used in place of what we're calling chronographs in the optical plane, right? Tell us a little bit about a starshade.
Yeah, and let me also say, as part of this talking about starshades, is that we mentioned there's 4 different studies leading towards the decadal. One of the other studies is something called HabX. Which
I'm sorry, HabX?
HabX, yeah, which is exoplanet focused, and is the study that's probably going to be more focused on starshades, in part because one of the key things about a starshade has to be quite far in front of the telescope, and it uses a technique called Fresnel diffraction to block out that bright star by basically putting this big 30, 40, 50 meter starshade 25 to 30,000 kilometers in front of the telescope. And the diffraction, there you can see a picture of it, the diffraction that happens, which is sort of it's as the light hits that starshade, the waves, if you think of sort of like the waves in the ocean, kind of cancel each other out when they get to the telescope, and that allows this very dark hole to be, dug, if you will. It creates a dark spot, which allows the planet to appear. So it's actually very similar. The physics is somewhat similar to a coronagraph, but instead of having the star blocked inside of an instrument inside of the telescope, it's blocked from the diffraction that happens from that starshade. The challenge with starshades, or one of the challenges, is moving them around the sky, and it turns out because of that, they're optimal. There's sort of this optimal size of a starshade in terms of repointing times that tend to favor telescopes that are a little smaller than LUVOIR, but the starshade also favors longer wavelengths at times, and so that's why we're still looking at it from the perspective of LUVOIR, is it may fill in some of the wavelength range, and it also may be an alternative way to solve this very difficult challenge of getting the contrast. The coronagraph technology still isn't fully at the place that it needs to be. So
good. That's where I was hoping you would go. So, what we were talking about, having little discs in the optical tube, or the optical path of the thing, will block out light, but it doesn't do as good a job as something like this, right?
Yeah, different chronographs and starshades have different strengths and weaknesses.
Right. Wait, Alberto, leave that back up. Don't. I want to go back.
Sorry. Okay.
Yeah.
Yeah. I'll bring it back in a sec.
Okay.
Yeah. So they have chronographs and starshades have different strengths and weaknesses. So the good thing about the chronographs is that they're quick to use. To go from one star to another, you just point the telescope. You just turn the telescope.
Right.
But in order for the chronographs to work, the telescope has to be really high quality and very stable. Because the chronograph lets in all that bright starlight that you don't want does enter the telescope, and that gives it a chance to bounce around in there, and that's why it's more stable the telescope, the more you control that bouncing around inside.
Okay.
That's why it has to be so stable. The starshades block all the light that you don't want before it enters the telescope. So in principle, they can give you better suppression of that bright star. But the downside is, in order to retarget it to another star, you have to flew it over this enormous arc in the sky of tens of thousands of kilometers.
You basically have to fly it around, don't you? You have
to fly it around the telescope, and as you can imagine, that's really slow. So they have different strengths and weaknesses. And so in a perfect world, my perfect world, the best exoplanet mission has both technologies.
Right. Okay.
But,
okay, so what Alberto had up that he promised he'd put back but didn't yet. No, not that one.
Sorry, I also put up an image of the chronograph so people have an idea of what kind of.
So what? All right, well.
There you go.
Well, that's an image that's been used with a coronagraph. That's what blocked out the star's light.
Yeah, and I want to point out that is a picture of that is a real picture of 4 super-Jupiters around a nearby young star. Those are real. That's a real picture of real exoplanets. And it's kind of amazing that that particular star actually has 4 super-Jupiters so close together. You wouldn't have thought that that could happen, but it does.
And I guess what I wanted to show here is that, what Aki was mentioning, that, since the coronagraph is inside the telescope and it gets sort of illuminated by the all the light that comes in, you see the noise at the center, right? So all these artifacts at the center are our ability to remove, to increase a contrast, if you will, or to remove the light from the star that we don't want to see, right?
Yeah, and all that muck in the middle of that image there, that was the leftover starlight that wasn't perfectly removed.
Correct. So that's a hard problem. If you're looking for something that is 10 billion times fainter than the parent star, that problem becomes very hard.
Yeah, you have to do a lot better than what's shown here.
Of course,
right.
Yes.
And so George Colwell has tweeting out. Let me just get it in because it's relevant to what we're talking about. He says he's asking how economically viable are star shades. We'll get to that in a minute, but this question is how much difference do they truly make? And that's what we're talking about here. There's a huge difference in the kind of things you can see with these star shades, making them, as Aki said, very useful in some respects where you're blocking the light out before you ever get to the telescope itself. So these things are huge, right, Lee? I mean, these things we're talking a really giant structure in space, aren't we?
Yeah. Although, look at the sun shield on JWST. We know how to make very large membrane-y type structures and do large deployables. And so for the most part, that's what a star shade is. Where the star shades get hard from the point of view of physically making them is actually on the edges. It turns out that there's very difficult requirements on the edges because the edges, there's the bright sun that's hitting the edge, and so you need very well-controlled edges. They're very thin. They're almost thinner than a razor blade.
Are you talking about the flower petal edges? Or
the flower
petal.
Right at the edge of the flower petal.
Okay.
There's sort of 2 things. One is the shape. How well do you have to control that overall shape? It's not nearly as difficult as building a large primary mirror. It's maybe 1,000 or 2,000 times easier than that, but it's much larger. So it's not an easy problem, but it is not considered to be the hardest of technology problems. However, the edges themselves are actually they're maybe the most challenging aspect of building the star shade because, of course, they have to fold up before the whole thing deploys, and they have to be these very fine structures, like I mentioned, that are thinner than a razor blade. So there are some technological aspects, and the other key aspect of it technologically is you have to be able to do what's called formation flying. You have to be able to point the telescope and the star shade and the star, you think of those 3 things, have to be in a line to a pretty good tolerance. That star shade has to be aligned almost about plus or minus a meter laterally. And so you have to do what's called formation flying, where the sensors in the telescope can see where that star shade is, feed that information to the star shade, and then tell the star shade how to do the station keeping to keep it aligned. And
the kind of pointing we're talking about here, then, the station keeping you just mentioned, as well as moving around with the telescope, is that on the same level as what, say, Hubble has to do when it points and slews to a different telescope? Does it have to be that steady? It
turns out, the telescope itself, probably is on order of the Hubble, milli-arc-second type pointing. But the real unique thing here is now you're putting the star shade in between and controlling that third body, if you will, to this plus or minus a meter type tolerance, and that's sort of a new thing.
Yeah.
It's not beyond the realm, of what one can do with thrusters, etc. But remember, you have this very large structure you're controlling, and in most cases, that structure, that large disk, is actually spinning in order to get an averaging effect to make the problem a little bit easier. So you have to be able to spin it. You have the pressure from the sun. They call that solar pressure, and then you have to keep all of those things aligned in a 3-body sort of way. And so people have been doing simulations. And the simulations say it should work, but it's the actual technological development is sort of still in progress.
I think you can imagine it this way, Tony. You have to keep the telescope in the shadow of the star shade, the shadow that the star shade casts, from the star, and then there's the star shade casting a shadow. You need to keep the telescope in the shadow. And it's plus or minus a meter. I don't actually think this is the hardest technological issue for star shades, actually, though.
No, it's not. Actually, we could probably have, Tony, a couple separate hangouts. One talking about coronagraphs, one talking about star shades.
Well, we did have one on star shades in the past, but I just wanted.
Yeah, we should do it again because there's a lot of stuff that has been done. I don't know if you can see the images that I put up.
I have you. I have.
We plan to return to it just so folks know, and this is a reminder to the folks in the audience. Our next Future Space Hangout, third Friday in August, will be on HabEx.
Oh, good. Well, there we go. So,
but one key point, I want to just make sure one key point is understood, is that when you're talking about a 12-meter telescope, the size of the star shade goes with that size of the telescope, as does the distance away that it is. So one of the real challenges for using a star shade with LUVOIR is that it gets really far away, and the amount of time it takes to move it from one target to another goes linearly with how far away it is. So in other words, the farther it gets, the longer it takes to repoint.
So a star shade you build for WFIRST, which it looks like this little cartoon is for, it would be at very much further away if you were doing it for LUVOIR.
Exactly. Exactly. So that's one of the reasons why we really want to solve this internal coronagraph and stability challenge. Is it really lets us be efficient in our surveying time.
Okay, well, I want to back away from star shades for just a minute and move on to another topic. But before I do, I just want to talk about, and in the context of the wavelengths, you had alluded to this, and this is something I'm very curious about. I get when you have a primary mirror, you want coatings that are optimally reflected for the wavelength you're looking at. Does the shape of a star shade change dramatically from a UV perspective versus an infrared one, for example, which would be the range? Would they be more or less the same?
Exactly.
Yeah.
Okay, so that's not such a big concern.
The size is what changes more than our distance, but not the shape of it. The shape.
So you could maybe scooch it out a little bit further if you're looking at one wavelength and bring it closer.
Correct.
Oh, okay, cool.
And understand, we're not talking about going all the way to the ultraviolet with the exoplanet work. When we're talking more focused on the visible wavelength range and maybe going a little bit into the near infrared. But the ultraviolet aspect of LUVOIR is really general class astrophysics, and it's the kind of stuff Hubble does, studying galaxies.
Excellent. Lee, you read my mind. Thank you for that beautiful segue. I now want to talk about this very topic. UV astronomy, these different wavelengths. Aki, can you tell us a little bit about how important that wavelength is, and why have we been, I don't want to say neglecting it, but come on now. We've got a lot of IR telescopes coming down the pike.
Yeah, well, the UV had a fantastic run through the Hubble years.
That's right. Still does.
Yeah, has and is continuing to have a fantastic run. Also, there was the FUSE satellite, if anybody remembers that one. I worked on it in grad school.
Alex, come on.
Yeah, so, there's a certain amount of turn taking that needs to happen. But the ultraviolet's, critically important, and you just can't do it from the ground because, very happily, we have an ozone layer that blocks the ultraviolet from hitting the ground, hitting the surface of the Earth, and that's super good news for us, but it's bad news for ultraviolet astronomers. So you have to go to space to do UV, and you want to go, in general, the way it works is if you want to look at things that are hot things, they tend to emit their photons at shorter wavelengths and in the ultraviolet. So it's sort of like
active galactic nuclei, quasars, things like that, right?
Yeah,
white dwarfs.
White dwarfs. And actually, I will point out too that there is exoplanet-related work in the ultraviolet. For example, if you were going to do transit spectroscopy in the UV, which people have done with Hubble, it allows you, when you do that, you look at the hottest layers of the planets, so like they're exospheres, and for really hot planets, those exospheres are actually escaping, so you can study evaporating planets if you do ultraviolet transit spectroscopy for exoplanets. So basically, you want the UV to look at things that are hot, that are energetic, and you just can't do that from the ground. And after Hubble, we will have no planned capability for ultraviolet astronomy. So
with large apertures, with very large apertures.
Well, we did have.
Well, with any apertures, there's not going to be anything after Hubble. So.
Right, after Hubble, there's nothing. I think because we had Galax for a few years, but then that's gone.
Yeah.
Right.
Galax, only does basically imaging. It doesn't do spectroscopy. So.
Correct, and it was large format, so you could actually do a whole sky surveys. I agree. So it's lower resolution.
Very small too. Yeah,
very small. Correct.
Yeah.
Not for imaging.
Yeah, really. So that.
Yeah. Well, what's remarkable about what's remarkable about this particular effort, I think, is the multi-wavelength proposal here. This idea that usually when we launch a space telescope, or it's good for one very narrow range of wavelengths, X-rays, for example, and by necessity. I mean, you really do want to optimize your instrument here. But is the technology gotten to the point where we can? I guess I want to go back to the coatings a little bit. I mean, is there a compromise at all, or are they really?
So Hubble spans this whole bandpass.
I know, but does it do it as well as if you had just launched a UV telescope, for example?
So the one thing we can do here that's, I think, a little bit new is we can actually push a little shortward. Hubble had aluminum mag fluoride coating, so it's an aluminum layer with mag fluoride on top. Mm-hmm. And at about, Lyman alpha thinks is the last of the peak of that, and by the time you're at 1150 angstroms, you pretty much dropping to zero on your coating reflectivity. Here we at least want to get down to 1,000 angstroms and possibly even 900. So we're going to try and push more to the fuse wavelengths in terms of performance.
We are not going to 900 angstroms later.
I'm sorry, 900 nanometers. No, 900. Well, 900 angstroms, but we may not. We need to see how far we can push the coatings. But so that's sort of the challenge there is how far we can push the shortward. On the longward, though, it really comes down to the telescope at the telescope temperature, and there we're likely to be a similar temperature as Hubble was, and we'll have a very similar thing where up until about 1.7 microns, the telescope temperature doesn't matter, and you get full performance. But once you get above 1.7 microns, as you get a little into the beyond in the near infrared, then the emission of the telescope, the heating just from the telescope temperature itself, starts to form a background, much like Hubble. Now, it's still reflective, and you can use the telescope longward of that wavelength, and in fact, there's some potential science we could even do all the way out into the mid-infrared, but it's not background limited in the sense that the mirrors are starting to emit heat that would keep you from being as background limited. Okay. But really, the wavelength push compared to Hubble is going to be on the shortward end.
Okay, good. So with the idea of going out, and this was wide wavelength range, in addition to that, is the location. You've heard us all talk about L2. L2 is like, I don't know, it's like Florida for space telescopes. It's where all of them go because it's a nice sweet spot for space telescopes. And I was talking with John Ehrenberg at Northrop one day about this, and he made a good point. He said that is an area where people have worried, for example, that if we launch something like James Webb Space Telescope, will it get damaged? It's 1.5 million kilometers away. We can't service it. What's going to happen if something runs into it, smashes into it, things like that. And L2, this point we're talking about putting these things, is a relatively clean and stable point, right, guys? Do any of you want to make some comments on the real estate here that we're going to be putting these?
Well, one thing I will say is that you brought up something about James Webb about not being able to fix it if anything goes wrong. That's not what we envision for LUVOIR. Right?
Oh, good point. Let's talk about that. Good.
Yeah, we envision LUVOIR as being in Hubble's tradition in several different ways, and one of those is that it would be serviceable and upgradable, most importantly. I mean, imagine what, there's no comparison between what Hubble's legacy would have been if all they had was their first generation instrument.
Oh, it's nowhere near the telescope it was in 1990. So
no. It's like many generations of instruments being upgraded and upgraded. I mean, that is one of the key vital points about Hubble's legacy. It really is.
That's very interesting. I did not know that.
Yeah, and that is what we want, and that's what we want for LUVOIR.
Yeah, and so
we want that thing to be a decade, a observatory for the century, to last decades, like Hubble did. Right. And it would be continually upgraded, and you could fix things if they broke. That's what we envision. That's what we're currently envisioning.
Okay, but are you worried about what's going to repair it?
About L2.
Oh, okay. Go ahead. Yes.
I was going to let you know that the reason why we put a lot of stuff there is because it's a very convenient point to be, but it's a semi-stable point. So things that are around L2 tend to want to drift away from L2. So it's a relatively clean place. At the same time, it trails Earth and the Moon as we go around the Sun. So we can, for JWST, for example, we can point always in the same direction. So we always view that system, right? So if you with minimum station keeping, we can keep spacecraft at L2.
Good.
Yeah, and probably the biggest thing, getting back to your earlier question about, are we worried about anything at L2? From Webb, we first of all, we've sent satellites to L2. I mean, WMAP's a great example, and Webb is going to L2. But one of the things that we spent a lot of time early on Webb working on was the question of micrometeoroids. So that's one of the things that you have to deal with. But these are very small little meteoroids, and for example, early in the development of Webb, when we were still looking at glass mirrors and lots of different mirror technologies, we actually did testing where we simulated micrometeoroids. We shot these little BBs at mirrors and looked at their effects to make sure that, for example, they wouldn't be a problem for the mirrors. The sun shield, for example, on Webb has 5 layers. For LUVOIR, it would be a multi-layer sun shield. And one of the reasons you do that is when the micrometeoroids pierce through, they make a series of small holes. One hole might be a problem, but by the time you have at least 3 layers, it's not a problem. And so you design and engineer things to be able to deal with that. But that's probably the most significant environmental thing that's at L2. I mean, there is some radiation. You have to worry about, electrons, et cetera. But for the most part, it's a pretty benign environment. And as they were mentioning, it's an extremely stable point.
Right. And are you worried at all, speaking of micrometeoroids and that thing we just got through talking about star shades, these gigantic, enormous things with presumably 1 layer? Are you worried at all about that?
They have to have multiple layers also.
Oh, they would too. I see. Okay.
Yeah. Same type of engineering would go on there, right?
Yeah.
Okay.
For exactly the same reason, because you don't want to poke a hole through it that lets light through.
Yeah, back in the day, I had a portable planetarium. It was called a Star Lab. It was great, but every time it got a little pinhole prick in it, you could see the light coming through every single time.
Well, when we brought WIFPIC 2 down from Hubble after the first servicing mission, the radiator, the outside surface of WIFPIC 2, always, because it had to radiate, always faced deep space, but it was in low Earth orbit. And we brought it back, the astronauts brought it down, we brought it to Goddard into the clean room, and we took it out, and it was pitted with micrometeoroids and you could see that in low Earth orbit where it gravitationally tracks things, I mean, there was just a really large number. So,
I'm sorry, did you say WIFPIC?
WIFPIC 2, yeah.
That was the Wide Field Planetary Camera 2.
Well, let me just say, first we brought down Wide Field Planetary Camera 1 after the first service mission, and then we brought down Wide Field Planetary Camera 2 after the second service mission. But they both essentially were pitted with these little micrometeoroids that in low Earth orbit are actually worse because the gravity attracts them. So even though you have them at L2, it's actually a more benign environment.
Okay, well, let me, I got a couple of tweets here that I want to read out loud. John O'Meara is commenting to me again about the UV. He says, if you want to understand the last 10 billion years of gas in and around galaxies, you need the UV.
Yep.
Can you guys comment on that just a little bit? Maybe Aki? Gas around?
Well, I mean, John is far more expert on this than I am, actually.
Okay. But you can imagine. I mean, I can add something that was.
Okay. Yeah.
I mean, one thing is you can imagine. You can imagine as galaxies, as galaxies form, and again, John could give a very, very good explanation of this because that's what he works on. But as galaxies form, there's a.
We should get him in the hangout.
We will definitely get him in a hangout. Also because I'm going to show you something that he just sent me before about LUVOIR. I'll show you before we leave that John sent me. But anyway, to make it long story short, as galaxies come together and they clash, you've seen these massive simulations where we have this constant merging of galaxies. The gas in between the galaxies and the gas around the galaxy gets heated to these very high temperatures, and so you actually take a look at those using UV as well.
Yeah. So again, the hot and the energetic, that's the realm for the UV.
Okay, yeah. So we're getting some good comments here. Again, this is from Andrew Planet. Hi, Andrew. Welcome back. It's good to see you again. Can you have some sort of coronagraph working in combination with the star shade? Do you get anything by using both?
That's a really good question, and we actually looked at that about almost 10 years ago now. Well, no, 6, 7, or 8 years ago now. And actually, it turns out you don't gain anything by stacking them, unfortunately.
Right.
They don't multiply, they just add, and it just doesn't help.
Oh, okay. Well, what did you just have up, Alberto? You put something up. Keep the L.
I put some time. Yeah, I put some up. I was
the bumper sticker that John O'Meara
made.
For,
there you go.
Yeah,
for
the
the
LUVOIR team.
Keep the love. I love it. That's great.
But the one thing you could do, I mean, as Aki alluded to earlier, you could have both, and you could actually use, for example, the Coronagraph for the survey and the visible wavelengths, and then maybe use your starshade for follow-up spectroscopy, maybe going to longer wavelengths.
Right, exactly. In a perfect world, you have both technologies. You don't use them simultaneously. You use them for what they're good at. So you'd use the Coronagraph to really quickly survey the sky to find the candidates, and then you could use the starshade to do the deep characterization spectroscopy, where you just want to stay on the star for a really long time. Starshades are good at that. So in a perfect world, that's what you do.
Okay, well, maybe I have a quick question. Maybe this is for you, Lee. We're talking when we talk about these astronomical point-and-shoot telescopes where you're moving things around, you have an observing program, people are applying for time, presumably, and you have an observing program going and where you're moving these things around. And let's say we also had a starshade doing the same thing. What kinds of technologies are going to be doing the moving of? Are we talking about jets? Are we talking about momentum wheels? What sort of things are we looking at to actually move these things around?
Yeah, I mean, we already use propellant and thrusters to do what's called station keeping.
Right.
And so, generally that's the kind of technology that does the physical moving. And one of the issues is, how much propellant do you have and how long does it last? You'll still have reaction wheels, for example, just to get your pointing set, and gyroscopes to know what you're pointing, and star trackers. But the thing that really moves you is going to be propellant and thrusters, and so you'll have to engineer it so that you have the right number of them, and that you you really have to optimize the use of the propellant. Now, one of the things though is, as you're moving that starshade from place to place, you can be doing other things. You can be doing general class science, or you can be doing coronagraphy or whatever. So you certainly can use that time, the telescope time, to do other things in parallel to it.
Okay, well,
the other thing you can think of is also there's a lot of probes that have been using, for example, solar electric propulsion, right? You can imagine things moving very slowly. So
yeah, we talked about that on Footsteps to Mars, didn't we?
Right. The alternative is maybe you have more than one starshade, right? So and
it's even possible. Let's say we don't want to build a starshade that is, designed for a full 12-meter telescope, because that may be, over 100 meters. You still could even consider having a smaller starshade, and even what's called stopping down the telescope internally. You could have a stop inside of the telescope, so that when you're using your starshade, your aperture is designed for that starshade size. So that's another trade that one could make, and that allows the starshade to be closer to the telescope.
Yeah, you're effectively faking a smaller telescope by stopping it down.
Sure. Okay, well, George Caldwell has two tweets that are kind of related. He's asking about other L points. He says, what about L1 and L3? L1 is the point that's on the other side of the Earth facing the Sun. That's where the SOHO spacecraft is. By the way, folks, that's the only other space telescope that has been up about as long as Hubble. It's been up 20 years. That has never been serviced, and to me it stands as an example of what's possible with these telescopes that are really far away. But L1 is on the other side, it's in between the Earth and the Sun. I don't think that's where we want to put space telescopes, do we? No. I mean, not like LUVOIR.
Keep in mind that when that big sun shield is up on James Webb, for example, the Sun and the Earth and the Moon are all on one side of that sun shield. Right. We want to block all three of those things. We don't want anything that's going to create instability, in terms of thermal. And there actually is a mission up at L1 right now called Discover, and it's taking some amazing pictures of the Moon as it orbits the Earth, and it kind of gives you a feel for what you might have to deal with if you were at L1. So yeah, it definitely would not be a good place to be. And likewise for L3, you'd have the same sorts of problems. L2 happens to be the one that's really great in terms of being able to put a sun shield up and having all three bodies on the essentially the warm side of it.
Right. Like I said, Florida.
For stability,
Okay.
yeah.
Okay. So, well, it's easy to get to, and it's nice and it's very stable. Can you have? Okay.
And there's a bunch of old spacecrafts there.
Oh, is that what I am? I see how it is. Okay, thank you, Alberto. Okay, well, let's talk about the future of the future. You guys are talking about these projects now. You're putting them on the design stage. You've got these documents written. I saw one called Living. What was it called? Living Earths. What was it? What was the name of that? Oh, I just
Cosmic Birth to Living Earths.
Cosmic Birth and Living Earth. Thank you. I just closed the window by accident. And so you've got these documents sort of outlining what you'd like to use a telescope like LUVOIR for. What's the next step? Where do we go from here? And how much time do you guys Does it have to be up like soon because of WFIRST and all that, or?
Well, the first thing we have to do, the first gate, the first hurdle, the first gate that we have here is actually to finish these studies, write them up, and submit them to the to NASA headquarters, who will then submit them to the national academies they'll be submitted in 2019 for judgment in 2020. And that's where, that's the mechanism by which the U.S. space science community, the U.S. astronomy community, decides what their priorities are moving forward. But, of course, the development time scale for a mission like LUVOIR is lots of decades. I've been saying to myself, I'll be lucky if it launches before I retire.
Okay, so if you are of the demographic I'm hoping to reach with these Hangouts at some point where maybe you're in high school, you're thinking about whether or not you want to work in astronomy.
Yeah, if you're in high school, that's a good time. That's a good time frame. If you're in high school or college, that's
this would be your telescope.
Yeah, that's true.
This would be something that would be built and designed with you in mind.
Actually, I want to underscore a point that Aki made. It's also the telescope for those folks in kindergarten or not even born yet. If it has the lifetime that we were talking about, it's several generations.
Yeah, it's going to last and last. But yeah, I mean, in some ways this is a telescope that is more for successors to use.
Right. And it's building on the technologies we've already put forth with building with James Webb Space Telescope as well as WFIRST. I would ask you some financing, what would this cost kind of things, but I get the feeling it's way too early for stuff like that. I think we're just planning the science that can be done along with the technology that's going to be required before we move on to that, right?
Yeah, we are not quite. Right now we're still in this study, we're still in the developing our science cases and our observation requirements. After that, then we actually have to do an engineering design, and then Lee and people like him come in. Until we actually know what the thing is we're building, I don't have the faintest notion what it costs.
Well, okay, but on a related note, and then we're running out of time, we'll let it go here, but you had mentioned earlier that you would like for LUVOIR to be serviceable. How do you plan a mission around something like that when you don't know even what it would be that might go out to service it with? How does that work?
So one thing you can do, which is easy to do early on, is to make things modular. So for example, if we can design, as we architect it, if we build instruments that one can access from the outside, think about when we serviced Hubble, how the astronauts were able to take instruments out and in from the outside. We cannot do that on Webb. There were reasons why it was really difficult to do it on a cryogenic telescope, etc. But with LUVOIR, the concept is that we can do that with the instruments and even with elements of the spacecraft.
I know, but Lee, when they designed Hubble, the space shuttle was around, and they said, okay, we'll use the space shuttle to do all this switching out. Yeah, what do you do now when you to say it's going to be serviceable? It's like saying.
One thing that's really different from 30 years ago when they were working on that is, first of all, robotics, right? And in fact, there's even a mission planned in 2020, which is going to demonstrate the ability to robotically refuel, a satellite in low Earth orbit. And there has been a lot of development in robotic capabilities for servicing. And we have not ruled out the possibility that even humans could go to L2. Remember, if we eventually want to go to Mars, it's not completely inconceivable. So there's a couple different possible ways one could service. What's important at this point from the point of view of architecting and designing is just to make it make sure it's serviceable.
Okay, by
and then
whatever.
we can monitor the technology.
Okay. Well, Harley, I'm sensing another hangout idea about this robotic.
Yeah, I just wrote it down, but I mean, I wanna inject some positive thinking here. I mean, do you really think that by 2035, the 2030s, we're not gonna be able to send robots out there? We better be able to do that. Because
I get it. No, I'm with you on this. And in fact, to build on JWST, when they were designing it, they had to say, well, what is it, we need to have the mirrors that do this, and we need to have this technology to do that. And then it had to be invented, right?
JWST is built robotically. Go and take a look at the videos that you have of how we assemble the mirrors. It's just on the ground, right?
Yeah, but my point is, it was depending on things that had not yet been even invented, and so we had to invent stuff for JWST to even work.
And WFIRST is also studying this idea of making WFIRST serviceable, which would be at L2. So WFIRST, WFIRST is an amazing proving ground for so many aspects of LUVOIR, the servicing, the coronography. So if WFIRST goes that route, that'll be yet another place where.
Well, I'm just going to put it out there, folks. If anybody is listening that's building these robotic craft, one of the ways you can test it in the 2020s is hopefully to go grab Hubble and bring it down for us, because a lot of people want that to happen. It'd be a good test of concept.
It's so heavy.
And so I know, but we need to have it back, and I know that it's going to be up there with Hubble or with James Webb Space Telescope. But when that's all over, instead of just burning it up, let's go get it. I'm just putting it up. Just saying. That's my.
Or we can put it in Florida.
L2. And put it in Florida. That's right. I have a place right here for it, so you can bring it out. All right. Let me just check Twitter one more last time. Thank you guys for using the hashtag. I appreciate it. Let's see. Laura Seward, I'm sorry, I won't pronounce your last name because I'll mess it up. She's saying, interesting discussion about space astronomy, or observatory servicing post-shuttle. Robotic servicing could work. Demo needed, in my opinion. Yes, I agree, and we just talked about some of that here. So, all right, well, I guess we will stop the hangout there. This has been God, there's so much we could talk about. But I want to thank all of you for tweeting and using the hashtag, and I hope next time there will be other chat technology available for you to use to help get easier access to our guests. But gosh, Dr. Lee Feinberg and Aki Roberge, I want to thank both of you for taking time out on this Friday to talk about some really cool stuff. So thank you both for joining us. And we hope as this mission progresses, or as this effort progresses, you'll come back and give us an update. Will you do that for us?
Yeah.
Sure, of course.
All right. Well, Harley, you've already given us a brief update. Can you remind some of us who've just maybe joined what we might expect in our next hangout?
Yep, we're going to talk at the next. We're going to have representatives of the fourth of the 4 strategic missions that NASA is assessing for consideration by the National Academy's Decadal Survey, and that'll be the HABEX mission as Aki described. Very powerful mission, specifically designed to look for exoplanets. So that is what it will concentrate on.
Awesome.
It should be very exciting. Also, we expect to have an upcoming hangouts on this one, robotics talk, in-space robotics.
Yeah, that's good.
Here, so a number of things coming up.
Great. So that'll be our next Future in Space Hangout in August. So I hope you guys will join us. Also join us the first Friday of every month where we talk about going to Mars. Footsteps to Mars Hangout is also the first Friday. So hope you'll join us on that. Alberto, thank you for joining us, and thank you for bringing your unique perspective as always.
Thank you. It was
and of course, we have the duck. We have the
that is our gravitational. We have to name this thing. It's our gravitational wave rubber ducky.
Why is it a duck? It doesn't make sense.
Exactly.
Because
we'll do that all. Maybe
that's another hangout.
No, it floats on the gravitational waves of space-time. That's what he does.
When we had the LIGO folks on about 3 months ago, they were using the example of waves in space-time. And they said it's like.
I should make a contest where people name the ducky.
Okay, that actually makes sense. I'm sorry.
We need a mascot for LUVOIR too, for the other studies. There you go.
Yeah, everything needs an app, but yeah, we'll do it. Okay, well, thank you guys very much. All right, folks, that's it for this hangout. Thank you all for joining us. Have a great weekend, and we'll hope to see you in August with another Future in Space hangout. On behalf of Alberto and Harley and our guests, thank you all for watching. And as always, keep looking up.